Hello and welcome to lecture 8. So, we are discussing about the component performance. In last lecture, we were discussing about the introduction to aero engine components. We started discussing about the intakes, where we started with the requirement of this intake. Then we were looking at different kinds of intakes, what we have used for turbofan engine, turboprop engine, turboshaft engine. Then we tried to analyze this intake as a fundamental component. We have taken the control volume approach for analysis. After analyzing this control volume, we realize we are having the performance of the intake that need to be evaluated, and this performance we have defined by using the different terminologies which are named as a diffuser efficiency, stagnation pressure ratio, or we can say pressure recovery factor, and we were discussing about the internal efficiency. Then we have given, or we were looking at the numerical. So, let us try to look at this numerical what we were discussing in last lecture. For the numerical, it says we are given with total to static pressure ratio and we are given with two different Mach numbers, and we need to calculate diffuser efficiency and stagnation pressure ratio for this both the cases. And we have discussed about the hint. With the given data, we want to calculate what is my stagnation pressure ratio and diffuser efficiency. So, let us look at, so if we look at here, we say the diffuser efficiency, it is a function of our pressure ratio, total to static pressure ratio to the power gamma minus 1 over gamma divided by gamma minus 1 by 2 into m infinity square. So, the data which is available with us is say P02 by P infinity is given 1.0254 and Mach number is 0.2. So, let us put this value. If I am putting my pressure ratio and Mach number as 0.2, I will get my diffuser efficiency to be 90%, 0.9. Let me put this on the chart. Here on x axis it is representing the Mach number, and on y axis this is representing my parameter called diffuser efficiency. Now, it says we need to calculate the stagnation pressure ratio. This stagnation pressure ratio we have derived the relation in last lecture, and that is what is a function of my diffuser efficiency and Mach number. So, if I put these numbers, we have calculated our diffuser efficiency as 0.9 and Mach number is 0.2. If we are putting these numbers, it says my recovery factor, that is what is, or pressure ratio factor, that is what is coming as 0.997. So, let me put that also on the chart. So, here if you look at, this is representing my diffuser efficiency and this is representing my pressure recovery factor or my total pressure ratio. Now, case 2, it says we are given with the pressure ratio of 1.453 and Mach number of 0.8. So, let us put these numbers here. If we are putting this pressure ratio as 1.453 and Mach number to be 0.8, it says my diffuser efficiency is coming 0.88. So, if I am putting that on the chart, it says this is coming to be 0.88. Okay. And my stagnation pressure ratio, if I calculate, that is coming as 0.953. So, let me put this as a number. So, here I want to express the interest, what we need to realize what is happening with our diffuser efficiency and what is happening with our stagnation pressure ratio. So, here if you look at, if I will be varying my Mach number from 0.2 to 0.4, 0.6, 0.8, you will realize my diffuser efficiency, that is what is decreasing. At the same time, if I am calculating my stagnation pressure ratio, that also is decreasing, but be careful, if we look at the numbers, it is different. So, do not get confused with what the information, that is what is being said to us. in terms of numerical, in terms of use of data. So, aircraft manufacturing companies, they will be getting the data from the intake manufacturer, they will be giving these numbers. Maybe in place of diffuser efficiency, they may be giving you total pressure ratio. Then you should not mislead the information. Okay. Now, this is what all we were discussing about the intake. Let us move towards the next component. If we look at very next component after my diffuser is my compressor. Now, here if you look at, we are having 8 stage of axial flow compressor. Since my flow is entering axially and leaving axially, this is what is my axial flow compressor. This compressor is comprising of, these are my rotors, and in between if you look at, the space is given, that space is for the placement of stator. So, combination of rotor and stator, that is what is defined as a stage. So, this compressor, it is comprising of 8 stages. This is having roughly pressure ratio in the range of maybe 8.3. Okay. So, let us target this component and let us try to understand what all we mean by this compressor. So, here if you look at, this is representing the high bypass ratio engine. So, very first component after my intake is not compressor, that is what is a big size fan. Since it is a high bypass ratio engine, that is the reason we are having our fan that having higher diameter. Here side by, if you look at, this is representing my low bypass ratio engine, where my diameter of the fan is smaller compared to this. Now, downside if you look at, this also are representing the compressor. So, this is defined as a LP compressor or low pressure compressor. In some companies they are using this terminology, in some literature they are using this terminology as intermediate pressure compressor. Next, what we have, that is also defined as a compressor, it is called high pressure compressor. So, it is called HP compressor. So, the terminology, that is what we are introducing here is LP and HP. Just remember one thing, LP does not mean it is generating low pressure, and HP does not mean it is generating high pressure. It is operating pressure. So, here this is operating at low pressure. So, you can say my entry pressure is lower, that is the reason why it is called low pressure compressor. After number of stages of my LP, the flow is entering inside my HP compressor. That means my operating pressure is higher. That is the reason why it is called HP compressor. Okay. Now, that is what is being connected with the shaft. Here if you look at, this is representing 2 spool configuration. 2 spool in the sense, my high pressure turbine, that is what will be rotating my high pressure compressor, and my low pressure turbine, that is what will be rotating my low pressure compressor and fan. We will be discussing what we mean by turbine when we will be discussing the component called turbine. Here if you look at, this is also representing the engine, aircraft engine, that is what has been developed by GE and Honda, it is HF engine. Here in this case if you look at, we are having a fan at the entry, that is what is having high bypass ratio, high aspect ratio blades. That is what will be followed by my compressor, it is my axial compressor. That is what will be followed later by the centrifugal compressor, and then it is entering inside my next component. So, you can say for the compressor in engine, it is not always that axial flow compressors are only present. There are engines in which you will be having both the combination of axial and centrifugal compressor. We will see when we go ahead what is the meaning and what is the reason why we are having this centrifugal compressor, that is what has been placed with. Now, here if you look at this fan, it is having the shape at the entry, if we look at, that is having the dimension to be large. You can say my entry diameter is large, my exit diameter is smaller. This is because what is happening, say for this fan, my pressure ratio will be in the range of 1.4, 1.6. The meaning of pressure ratio is my entry pressure and exit pressure. So, it says my exit pressure divided by my entry pressure, that is what is defined as my pressure ratio. Since my exit pressure is larger, we can say my density also will be higher. Now, the continuity equation says my entry mass flow rate, my exit mass flow rate, they both need to be same. The meaning here is at the entry, suppose if I consider it is density into area into velocity, and at the exit I will be writing same as say density into area into velocity. Suppose if I consider my velocity I am assuming to be constant, what will happen? Because my pressure, that is what is higher at the exit, that is the reason my area is smaller. So, you can say here in this case I am having converging passage. Same way if we look at the passage here for HP compressor, that is also having my entry area to be large and my exit area to be smaller. Okay. So, for compressor we need to remember this thing. What exactly makes these blades to be of high height or maybe having higher say height of the blade at the entry and lower height of the blade at the exit is because of change of pressure, which will be bringing the change in density. Okay, there is no other reason. Now, just look at how the construction is here. If you look at very first component what we have, it is called inlet guide vane. The purpose of this inlet guide vane, it is to guide the flow. Okay. So, if we look at the engine manufacturing companies, they are placed on both the side of Pacific. We mean it is maybe in say European country, and on other side we are having US. So, they both have different identity and they are having different design strategies. So, if we look at American engines, they are preferring with the inlet guide vanes, and if we look at say European engines, they are not having inlet guide vanes. They both have their own philosophy. So, if you want to understand what is the reason why all those stuffs, you just go in detail. Since this course it is not been for explanation of the compressor, that is the reason we will not be discussing about that part. Next component what we have is my rotor. So, the rotor what it is doing? It is doing work on my working fluid. My working fluid is air, and that is what is by mean of generating the lift. Now, the question is what we mean by lift. So, if we look at the blades of this compressor, they are having aerofoil shape. There is a reason behind selection of this blade shape to be aerofoil shape. So, if we look at here, this is representing two aerofoils of two blades at particular station. What we mean I will discuss in later part. What we know, we have understanding that this surface, that is what we are defining as a pressure surface. This surface we are defining as a suction surface. This is representing my leading edge. Other side I am representing, it is called trailing edge. Now, on my pressure side I am having high pressure, on my suction side we are having low pressure, that is what is generating the differential pressure, and because of that differential pressure we are having lift force. That is what we have studied in our basic understanding of aerodynamics. The same logic it is being used here. Now, what we are using here is we want to utilize this lift force. So, here if you look at these blades are made up of number of aerofoils, and each aerofoil, that is what is generating the lift. Now, in order to utilize that lift force, what we need to do, when the fluid it is entering through this passage, this lift force we are utilizing for compressing our gas or say air. Okay. Now, in order to do that, we need to rotate our wheel, and this rotation we are doing from suction surface towards the pressure surface. So, this will be the direction of my rotation. The meaning here is the air that will be passing through this passage, that's what will be subjected to say compression action, or we are doing the work on our working fluid by utilizing this lift force. Okay. Now, here if we look at, this is how my flow passage, that's what will be behaving with. So, in overall, what is the purpose? It says my rotor blade, it will give the acceleration to my flow, then this will be converted into the kinetic energy. That kinetic energy we are converting into pressure. So, here if we look at carefully, this is my inlet area and this is my exit area. So, if we look at this passage area is looking like a diffuser, because my entry area is lower, exit area is higher. So, it will act as a diffuser and it will diffuse the flow, means it is increasing my pressure. So, at the entry I am having pressure say P01, at the exit I will be having pressure P02, that P02 is higher. So, we can say my compressor is working under adverse pressure gradient, because my entry pressure and exit pressure, they are different. My entry pressure is lower, my exit pressure is higher. Now, this kinetic energy what flow is coming with, that will be passing through the next blade, that is what is called stator blade. So, this is a stationary blade. Rotor means it is a rotating blade and stator, that means it is a stationary blade. That also is decelerating the flow, and as we have discussed few minutes back, we are having our entry area and exit area, that is what is different. So, I am sure this is what will be giving you the idea of my axial flow compressor. Now, the situation is, since it is working under adverse pressure gradient and this aerofoil is a fragile body, it has more chances to get separated, the flow to get separated from the suction surface or the pressure surface. That is the reason why this turning of this aerofoil, it is not permitted too much, and that is the reason why we are not having the single stage, that is what is generating very high pressure ratio. Suppose if I consider, we have discussed about our engine, what we have started with, that is having the pressure ratio of 8.3:1 and which required 8 number of stages. So, this is the reason why we are having our axial flow compressor with more number of stages. Okay. Now, here if we look at, this is what we want to look at the blade. So, here this is what is representing the blade of my rotor, this is my entry passage and this will be my exit passage. Suppose if I consider I am representing in a conventional way, this is my rotor and stator. Let me take this as my mid section, it is nothing at the middle of my whole blade, and I say this is what is made up of number of aerofoils. At each station we are having different aerofoils. Now, those who are very much interested for this compressor, just go through our earlier NPTEL lecture, the aerodynamic design of compressors and fans. That is what will give you more detailed understanding, and I am sure that is what will be helping you. It will give you joyful moment, at the same time you build your confidence, you make yourself more employable to the requirement by the industries. Okay. Now, here at one station I will be putting that as say section. So, here if I will be cutting, it says this is my passage, and in overall if I look at the whole blade passage, that is what is made up of this diffusing passage. So, that is where we are having the diffusing action, that is what is because of rotation as well as the passage area between two blades. Okay. Now, let us try to look at what is how my pressure and temperature, that is what is varying along my stage. So, here if you look at, this is what is representing my rotor and the stator. This is my entry condition, I say station 1, station 2 and station 3. So, this is my entry pressure, I say P1. My flow, that is what will be entering with some velocity, say C1, and if I will be adding this together, that is what will be giving me my total pressure. Okay. So, P01 is my total pressure at the entry. Now my rotor, that's what is increasing my pressure. So this is representing the pressure rise from P01 to P02. This is representing my total temperature T02. If we consider the stator, that's what is, it is a stationary device, no work it is been done by the stator. So we can say the process of diffusion which is happening, or process, that's what is happening in my stator passage, it is adiabatic process, and that's the reason I say this is represented by say 03 stage. It says my T02 and T03 they are same. Again, since this is what is a solid body where we will be having the frictional losses which are happening, and that's the reason my total pressure, that's what will be dropping. And here this is representing my exit pressure from the stage. Now if I will be putting this in terms of C3 square by 2 Cp, that's what will be giving me my outlet pressure from the stage, it is P3. Same way, if I will try to put my C2 square by 2 Cp, that's what will be giving me my static pressure at state 2. State 2 is exit of my rotor. If I will be connecting this together, so it is representing the rise of pressure from P1 to P2, that's what is happening inside my rotor, and from P2 to P3, that's what is happening inside my stator. And here if you look at my compression process, that's what I am representing from 01 to 03 dash, that's what is my isentropic process, and from 01 to 02 or 03 if we are putting, that's what is representing my actual process. So just realize one thing, my isentropic process and actual process, it says we are having some losses which are happening, and that's what is giving the irreversibility to my flow, and that's what will lead to increase the entropy. So let's look at this part. Here in this case, if I want to calculate what is the amount of work that's what is required by the compressor, then that's what is given in thermodynamic term as mCp T03 minus T01. Since my T03 and T02 are same, so I can write down mCp delta T0. Now as we were discussing earlier, we are having the compressor which are having axial and centrifugal compressor combination. So very first pattern it was given by Frank Whittle, in which he has described the engine which is having multiple stages of axial compressor, that will be followed by the centrifugal compressor. So let's try to look at what is the meaning of that. Suppose if I say I am looking for the low pressure ratio, it says this is representing my low pressure ratio stage. So I will be having number of axial flow compressor stages. As we have discussed, since I am having the problem with the fragile body, that's what is because of aerofoil, which has more chances for the flow separation, and in order to avoid that situation, we are having this number of stages to be higher. Here on right hand side, if you look at, for the same pressure rise, I can use single centrifugal compressor. Okay. This centrifugal compressor, it has its own limitation. Here if you look at my area for the flow to enter, that's what is large. The meaning is I can handle large mass flow rate. This is representing the entry of my centrifugal compressor. Since this area is lower, so I cannot handle large mass flow rate. That's what is the limitation with the centrifugal compressor. If I want to have this kind of entry area, then my size and weight of the centrifugal compressor, that will be very high. To avoid that kind of situation, we are not using centrifugal compressor these days. Yeah, earlier people they have used. When we will be discussing about the turbojet engine, that time we will discuss this aspect. Now the situation is, it says if I want to have high pressure ratio, then I need to increase the number of stages. What is happening here? When I am increasing my number of stages, my rear stages, that's what is getting smaller and smaller. So the height of my blade, that's what will be reducing. If this is reducing, it says I am having the aerodynamic blockage problem. One more problem what we have here, that's what is in terms of the tip clearance. So this is putting the limitation in terms of increasing the number of stages. So, alternative, it says suppose I want to reduce the length of my engine, I want to reduce the weight of my engine, and if I want to reduce the size of my engine, then I can incorporate with the axial centrifugal compressor configuration. So, what problem we were having in terms of say height of the blade to be smaller, that can be rectified by using this axial centrifugal compressor configuration. It has many benefits. Here if you look at, my blade height is not an issue. You can see the size of my engine, that is what is reduced, the weight of the engine, that also will be reduced. And here if you look at, people they are more interested in the efficiency. Here in this case, if I will be going with the centrifugal compressor alone, my operating mass flow rate, that is what is smaller, we have discussed earlier. Suppose if I will be going with the axial kind of configuration, where for the medium mass flow rate, I will be having my efficiency to be lower. So, I need to have some machines which will be operating in this range, where the axial centrifugal compressor that will be coming into the picture. So, this is what is representing the cut section of one of the engine, that is what is being used for the Honeywell turboprop engine, where we are having two centrifugal compressors, that is what is being placed. Here we are having axial centrifugal compressor stage. Now, very important and fundamental part, that is what we need to discuss for the compressor is in terms of the fundamental equation, that is called Euler's equation. We say a compressor in which we are adding the power in order to do the work. Now, this work, that is what will bring the change of energy and the tangential momentum. So, here if you look at, this is representing my stator, that is what will be followed by my rotor. Okay. This is representing my radial direction. So, let us see if I will be putting my cut section here, and if I look at my aerofoils, they will be looking like this. They are my stator blades, and in this direction I am having my flow, that is what is entering, I say its axial direction, and this is what is representing my tangential direction. Here this is what is my rotor, and as we have discussed, that is what will be rotating from my pressure, say that is what is rotating from my suction side to the pressure side, because we want to do work on our working fluid. Now, here if we look at carefully, it says suppose if I am assuming I am having machine which is having entry radius of R1 and exit radius of R2. Okay. I will be putting my tangential velocity component at the entry is Cw1 and tangential velocity component at the exit is say Cw2. So, if we are applying the conservation law of our angular momentum, it says the rate of change of angular momentum, that is what we are defining as a torque for the rotating machine. So, that is what is given by m dot into Cw2 R2 minus Cw1 R1. Now, we are having this blade which are rotating at some angular speed, say omega. If I will be putting, if I multiply my torque with the angular velocity, that is what is giving me my power to be Cw2 U2 minus Cw1 U1. Here in this case, it says if my tangential velocity, that is what is increasing across the blade row, that means positive tangential velocity defined in the same direction of my rotation, then the work it is been added to the flow, and that is what is called compressor. This is what is very important. Here if you look at, this is what is representing my centrifugal compressor, where my entry radius is lower, my exit radius is higher. If I will be taking my axial machine, my radius will be varying as per the requirement from entry to exit, and we are having tangential velocity component. This will be very important when I will be discussing about different configurations of the engine. Now, let us try to analyze this compressor using my control volume approach, what we have applied for our intake. Same way we are using this for centrifugal for this compressor. Let us say my entry condition here, it is 2, exit condition is 3. My entry mass flow rate is M2 and exit mass flow rate is M3. Suppose I am assuming there is no bleed or the leakage. I say my Q is 0 because my compression process we are assuming to be adiabatic process, and here in this case we are giving the work to our rotor, and that is the reason my shaft, that is what is crossing the control volume. So, boundary and transmit the work to the compressor, and that is the reason we say my work, that is what is being done on my system, and that work done we are defining, we are showing as negative value. So, here if you look at, this is representing my Q equal to delta E minus W, there is no heat transfer. So, it says my work, that is what will be coming in terms of delta E. What it says, the change of total enthalpy, that is what will be equal to my work delivered to the compressor. So, let us try to look at that and understand in terms of our fundamental equation, steady flow energy equation. This is what is representing our fundamental equation here. Now, let us put this compressor on TS diagram. As we have discussed earlier, the compression process, that is what will be represented in terms of say isentropic process, which is rising the pressure from P02 to P03, and here this is what is representing my actual compression work. We see because of irreversibility my entropy, that is what is increasing, and that is what will be giving me my exit temperature to be higher compared to say my isentropic temperature. So, here this is what is representing my isentropic work done, and this is representing my actual work done. Now, again as we have discussed, we always try to criticize our component, any device in terms of efficiency. So, for this compressor, people they used to define the efficiency as isentropic efficiency, and if we are going in more detail with the number of stages, that is what has been defined as a polytropic efficiency. So, let us look at what is the meaning of that. Now, what all irreversibility we are discussing, it says in actual process we are having the wall friction, that is what is acting on a medium through boundary layer. Suppose if I consider my flow, that is what may go transonic or supersonic near the tip region. Under that condition we will be having the losses because of the formation of shock. So, we can say we are having the combination of effect in terms of viscosity, that is what is we are defining in terms of boundary layer formation, wake, vortex seeding, or maybe shock formation. And if that is what is the case, we can say this process will not be adiabatic and reversible, and we can say that is what will lead to increase the entropy. And if I consider this as a case, that is the reason we say my temperature what we will be getting for the same pressure ratio at the exit in actual condition will be higher than that of my isentropic process. So, let us look at how do we use this information. So, as we have discussed, we will be criticizing our compressor by say efficiency. This efficiency, it is been defined as ideal work done by actual work done. Be careful, it is not the reciprocal, because we are using this device, it is a power consuming device. We are supplying the energy, and that is the reason why this ratio is taken as a ideal work divided by actual work. This ideal work we can say it is represented by H03s minus H2 divided by H03 by H02. Now, this is what can be represented in terms of isentropic relation. Let me put this P03 by P0T, I am putting that as say my pressure ratio. By temperature I say T03 by T02, that is what I am defining as my temperature ratio. So, if I will be putting all together, it says my efficiency of the compressor, it is a function of pressure ratio, it is a function of my temperature ratio. Okay. And this temperature we have decided, we have calculated, and it says my actual temperature, that is what will be higher than that of my ideal temperature ratio. Now, in order to look at the compressor, this is what is representing. Suppose I have 10 stages, that is what is generating the pressure ratio, suppose say 12. So, this TS diagram, that is what is representing that kind of situation. We can say this is representing all stage configuration or overall pressure ratio. Now, what we realize, we are having the compressor, it is made up of number of stages. So, I will be splitting that into number of stages. Suppose say I want to have my pressure rise from P02 to P03, I will be dividing that into maybe 3 stages. If this is the case, I can say this is representing my isentropic temperature rise for the first stage. This is representing my actual temperature rise. That is what will be the input for my next stage. So, here this is representing my isentropic temperature rise and this is representing my actual temperature rise. Same way, this is what is your scenario. So, here we need to observe the thing, very important thing, that is what is happening in terms when we are going with the multi-stage configuration, or we can say per stage configuration. What is our observation? Here if you look at, this is what is representing my isentropic temperature rise for say multi-stage configuration, and here this is what is representing my isentropic temperature rise when I am considering single stage or single configuration. So, here what efficiency we are defining, that is what is defined as a polytropic efficiency, and here this is what is representing my isentropic efficiency. Okay. So, here if we look at my vertical distance, that is what will be increasing with the increase of entropy. So, summation of my all isentropic temperature rise, that is what will be coming greater than that of my single stage. So, let us try to analyze what is the use of this information. Now, we can say now the efficiency that is defined as a polytropic efficiency. What we know, our isentropic efficiency we can write as delta H0S by delta H0. Suppose if I am taking say per stage or small efficiency or polytropic efficiency, that is what is represented by dH0 by ds. We know our second law of thermodynamics. If I am considering my entropy, that is what is constant, or say there is no change of entropy, ds equal to 0, then we will try to find this polytropic efficiency in a differential form. And if I will be simplifying and integrating the term, it says we will be getting the equation. It says my compressor efficiency, it is a function of my pressure ratio, it is a function of my polytropic efficiency. Now, what we have derived earlier, that is what is say my efficiency of the overall stage, that is what is say my isentropic efficiency, it is a function of my pressure ratio and my temperature ratio. So, this is what is very important information, that is what we need to go with. Now, in order to understand what is the meaning of isentropic efficiency and polytropic efficiency, we will take one numerical. Okay. So, take this numerical as say compressors of 2 gas turbine engine as a pressure ratio of say 10 and 16. Calculate the adiabatic efficiency if the polytropic efficiencies are 90% and 92%. So, it says we are having two different pressure ratios 10 and 16. Their polytropic efficiency is 90% and 92%. So, let us get the hint for that. What all we know? It says the information given to us is in terms of pressure ratio and polytropic efficiency. We want to calculate what will be our adiabatic efficiency. I am sure this you can do in the reference of what all we have discussed about the axial flow compressor, what all we have discussed about the polytropic efficiency and our adiabatic efficiency. So, this numerical we will be solving in next lecture. So, let us sum up what all we have discussed today in terms of our compressor. We realize our compressor is say axial flow compressor, most widely used for almost all aero engines. It's not that we are not using the centrifugal compressor. We have seen the engine where we are having combination of axial compressor and centrifugal compressor. Then we were discussing about how my process in terms of HS diagram is happening for the compressor. Then we have done our analysis for say control volume approach, and we have come up with two important properties. One, it is my isentropic efficiency or adiabatic efficiency, and second, that's what is my polytropic efficiency. So in next lecture we will be discussing about the next component in detail. Thank you very much for your kind attention. If you have any query, you can drop the email that will give the clarity for your questions. Thank you very much.